Greetings to dear friends, thank you for choosing the BigDark channel for teaching scientific content. Please do not forget to subscribe, like, and comment to support the channel. Solar wind. The solar wind is a stream of charged particles released from the upper atmosphere of the Sun, called the corona. This plasma mostly consists of electrons, protons, and alpha particles with kinetic energy between 0.5 and 10 keV. Superposed with the solar wind plasma is the interplanetary magnetic field. The solar wind varies in density, temperature, and speed over time and over solar latitude and longitude. Its particles can escape the Sun's gravity because of their high energy resulting from the high temperature of the corona, which in turn is a result of the coronal magnetic field. At a distance of more than a few solar radii from the Sun, the solar wind reaches speeds of 250 to 750 km per second and is supersonic, meaning it moves faster than the speed of the fast magnetosonic wave. The flow of the solar wind is no longer supersonic at the termination shock. Other related phenomena include the aurora, northern and southern lights, the plasma tails of comets that always point away from the Sun, and geomagnetic storms that can change the direction of magnetic field lines. Observations from Earth. The existence of particles flowing outward from the Sun to the Earth was first suggested by British astronomer Richard C. Carrington. In 1859, Carrington and Richard Hodgson independently made the first observations of what would later be called a solar flare. This is a sudden, localized increase in brightness on the solar disk, which is now known to often occur in conjunction with an episodic ejection of material and magnetic flux from the Sun's atmosphere, known as a coronal mass ejection. The following day, a powerful geomagnetic storm was observed, and Carrington suspected that there might be a connection. The geomagnetic storm is now attributed to the arrival of the coronal mass ejection in near-Earth space and its subsequent interaction with the Earth's magnetosphere. Irish academic George Fitzgerald later suggested that matter was being regularly accelerated away from the Sun, reaching the Earth after several days. In 1910, British astrophysicist Arthur Eddington essentially suggested the existence of the solar wind, without naming it, in a footnote to an article on Comet Morehouse. Eddington's proposition was never fully embraced, even though he had also made a similar suggestion at a Royal Institution address the previous year, in which he had postulated that the ejected material consisted of electrons, whereas in his study of Comet Morehouse he had supposed them to be ions. The idea that the ejected material consisted of both ions and electrons was first suggested by Norwegian scientist Christian Birkeland. His geomagnetic surveys showed that auroral activity was almost uninterrupted. As these displays and other geomagnetic activity were being produced by particles from the Sun, he concluded that the Earth was being continually bombarded by rays of electric corpuscles emitted by the Sun. He proposed in 1916 that, from a physical point of view, it is most probable that solar rays are neither exclusively negative nor positive rays, but of both kinds. In other words, the solar wind consists of both negative electrons and positive ions. 3 years later, in 1919, British physicist Frederick Lindemann also suggested that the Sun ejects particles of both polarities, protons as well as electrons. Observations from space. In January 1959, the Soviet spacecraft Luna 1 first directly observed the solar wind and measured its strength, using hemispherical ion traps. The discovery, made by Konstantin Gringaz, was verified by Luna 2, Luna 3, and the more distant measurements of Venera 1. 3 years later, a similar measurement was performed by American geophysicist Marcia Neugebauer and collaborators using the Mariner 2 spacecraft. The first numerical simulation of the solar wind in the solar corona, including closed and open field lines, was performed by Neumann and Kopp in 1971. The magneto-hydrodynamics equations in steady state were solved iteratively starting with an initial dipolar configuration. In 1990, the Ulysses probe was launched to study solar wind from high solar latitudes. All prior observations had been made at or near the solar system's ecliptic plane. In 2018, NASA launched the Parker Solar Probe, named in honor of American astrophysicist Eugene Parker, on a mission to study the structure and dynamics of the solar corona, in an attempt to understand the mechanisms that cause particles to be heated and accelerated as the solar wind. During its 7-year mission, the probe will make 24 orbits of the Sun, passing further into the corona with each orbit's perihelion, ultimately passing within 0.04 astronomical units of the Sun's surface. It is the first NASA spacecraft named for a living person, and Parker, at age 91, was on hand to observe the launch. Acceleration. While early models of solar wind relied primarily on thermal energy to accelerate the material, by the 1960s it was clear that thermal acceleration alone cannot account for the high speed of the solar wind. An additional unknown acceleration mechanism is required and likely relates to magnetic fields in the solar atmosphere. The Sun's corona, or extended outer layer, is a region of plasma that is heated to over a megakelvin. As a result of thermal collisions, the particles within the inner corona have a range and distribution of speeds described by a Maxwellian distribution. The mean velocity of these particles is about 145 km per second, which is well below the solar escape velocity of 618 km per second. However, a few of the particles achieve energies sufficient to reach the terminal velocity of 400 km per second, which allows them to feed the solar wind. At the same temperature, electrons, due to their much smaller mass, reach escape velocity and build up an electric field that further accelerates ions away from the Sun. Fast and slow solar wind. The solar wind is observed to exist in two fundamental states, termed the slow solar wind and the fast solar wind, though their differences extend well beyond their speeds. In near-Earth space, the slow solar wind is observed to have a velocity of 300 to 500 km per second, a temperature of 100 mK, and a composition that is a close match to the corona. By contrast, the fast solar wind has a typical velocity of 750 km per second, a temperature of 800 mK, and it nearly matches the composition of the Sun's photosphere. The slow solar wind is twice as dense and more variable in nature than the fast solar wind. The slow solar wind appears to originate from a region around the Sun's equatorial belt that is known as the streamer belt, where coronal streamers are produced by magnetic flux open to the heliosphere draping over closed magnetic loops. The exact coronal structures involved in slow solar wind formation and the method by which the material is released are still under debate. Observations of the Sun between 1996 and 2001 showed that emission of the slow solar wind occurred at latitudes up to 30 to 35 degrees during the solar minimum, the period of lowest solar activity, then expanded toward the poles as the solar cycle approached maximum. At solar maximum, the poles were also emitting a slow solar wind. Coronal mass ejection. Both the fast and slow solar wind can be interrupted by large, fast-moving bursts of plasma called coronal mass ejections, or CMEs. CMEs are caused by a release of magnetic energy at the Sun. CMEs are often called solar storms or space storms in the popular media. They are sometimes, but not always, associated with solar flares, which are another manifestation of magnetic energy release at the Sun. CMEs cause shock waves in the thin plasma of the heliosphere, launching electromagnetic waves and accelerating particles, mostly protons and electrons, to form showers of ionizing radiation that precede the CME. Solar system effects. Over the Sun's lifetime, the interaction of its surface layers with the escaping solar wind has significantly decreased its surface rotation rate. The wind is considered responsible for comets' tails, along with the Sun's radiation. The solar wind contributes to fluctuations in celestial radio waves observed on the Earth, through an effect called interplanetary scintillation. Moons and planetary surfaces. Mercury, the nearest planet to the Sun, bears the full brunt of the solar wind, and since its atmosphere is vestigial and transient, its surface is bathed in radiation. Mercury has an intrinsic magnetic field, so under normal solar wind conditions, the solar wind cannot penetrate its magnetosphere and particles only reach the surface in the cusp regions. During coronal mass ejections, however, the magnetopause may get pressed into the surface of the planet, and under these conditions, the solar wind may interact freely with the planetary surface. The Earth's moon has no atmosphere or intrinsic magnetic field, and consequently, its surface is bombarded with full solar wind. The Project Apollo missions deployed passive aluminum collectors in an attempt to sample the solar wind, and lunar soil returned for study confirmed that the lunar regolith is enriched in atomic nuclei deposited from the solar wind. These elements may prove useful resources for lunar colonies. Outer limits. The solar wind blows a bubble in the interstellar medium, the rarefied hydrogen and helium gas that permeates the galaxy. The point where the solar wind's strength is no longer great enough to push back the interstellar medium is known as the heliopause and is often considered to be the outer border of the solar system. The distance to the heliopause is not precisely known and probably depends on the current velocity of the solar wind and the local density of the interstellar medium, but it is far outside Pluto's orbit. Scientists hope to gain perspective on the heliopause from data acquired through the Interstellar Boundary Explorer (IBEX) mission launch. Thank you for being with us until the end of the program. Be sure to mention your opinions about the educational video in the comments section.